insofar as resources were transferred from, just for example, from C to A, what I've done is I've secured my spot in the system. My spot in the system is now secured, right? Without making that transference, I would have, you saw the flow, right? I would have inevitably eliminated both myself and state A, and B would have ended up dominating the system. It would have gone from a three-state system to a two-state system, which would, the two-state being A and B, after the elimination of C, to a one-state system, just B at 300, right? So it's important to recognize that this example, the initial example where we have 120, 180, is, and I want to make this clear now, right? This affairs where we have 120, 180, right? This is a representation of a system stable, but not a resource stable state of affairs. So this is only system stable, right? This is only system stable. It is not resource stable. Why? Because resources have to be transferred in order to secure my position in the system. Specifically, 30 points worth of resources need to be transferred. Obviously, this is all sort of theoretical, right? But this is the language. I'm not making this up, right? And that 30 points would need to be transferred in order to secure my position. So, system stable, not resource stable. Okay. What's the next one? Did I do? Okay. So now the next thing is to look at more than three states. So just to review, just quickly before we go on, in a two-state system, we recognize that the only way to have stability of any kind within a two-state system is for the total distribution of resources to be shared equally. If we are talking about a two-state system, it is impossible to have a system stable only two-state system. That cannot happen, right? And I showed and I explained that, right? A two-state system is only stable when it is both resource stable and system stable. It is impossible to have a system stable only two-state system. That can't happen. Anything else, any other appropriation of resources aside from 150 or whatever the number is, anything other than a division right down the middle destabilizes the system, right? It's the destabilization of the system. On a quick side note, my wife and I just wrote precisely on this issue with respect to national security and destabilization within other governments. The book will be out in probably summer. But destabilization becomes problematic, obviously, in a two-state system where resources, if you buy into this theoretical construct, where resources aren't shared and divided equally. Second point, in a three-state system, it is the case that you can have both forms of resource and system stability, and you can have only system stability without resource stability. The question then becomes, can you have, since we know you can have system stability without having resource stability, which was the example I showed before, and we know we can have both system stability and resource stability, the question is, can you have resource stability without system stability, right? And the point is, meaning that there is no transference, there's never going to be a transference between states, but a state is going to be ejected. The point is, no, you couldn't, right? There isn't a way to have resource stability without also having system stability. System stability is entailed within resource stability. So if I say that the state is resource stable, it has to be system stable, right? However, you can have, as we just saw, you can have system stability but lack resource stability, as in the example where 30 units were transferred from C to A, right? That was system stable, no one was ejected. However, it was not resource stable, right? So you can have system stability without resource stability, but you cannot have resource stability without system. And I'll actually write this down, because that might sound crazy. and I'll just abbreviate this SS and RS. Right, so you can have SS without RS, but you cannot have resource stability without system stability. Right? So you can have system stability without resource stability, but you cannot have resource stability without system stability. So it sounds like word tricks, but as you can see from a theoretical stance, it makes perfect sense, right? If we are transferring resources, we're doing so to keep the system stable, right? So we can talk about that, and I actually want to read a section because I think he speaks on this on page 181. He goes, the example of systems have a total of 300 resources. A system is resource stable, right? Is resource stable if no resources are ever redistributed in the system, right? A system is system stable if no state is ever eliminated, which we said. A system is resource stable. If a system is resource stable, it is then system stable by definition, right? So if it's resource stable, right, then it has to be system stable, right? So you cannot have a case where it's resource stable and it's not system stable, right? It has to be. Okay. Next point. So let's look at, so we did 3, now we're going to do any number greater than 3, right? Anything greater than 3. So when we're talking about state systems greater than 3, it doesn't really matter. So resources, and I'm not going to draw out all the circles because it's not just 4, it's up to, 140, whatever. Resources in system, resource and system stability in more than 3 state system. So how is it that we can have both resource stability and system stability in a system that has more than 3 states involved? Well, obviously, all we need is for just one of those states, it doesn't matter how many states they are, just one of those states to have half the distribution of the total resources, right? So whatever the total resources are, right? So let's say total distribution of resources equals X. Then at least one state, right? At least one state has to have half of that, half of X, right? If at least one state has half of X, then we recognize that the state is going to be both system stable and resource stable, right? So whatever the distribution may be, and I'll give you an example. Actually, this is Moreau's example. The example is 150. So let's actually do it. A, B, C, D. Now, granted, this can go much further than 4, but just to show you greater than 3. So the distribution is 50, 150, 150, 130, 20. Make sure I wrote that right. 150, 130, 20. Right? So this is both. This is a state system in which we're talking about greater than 3. It happens to be 4. At least one state has half the distribution. Total distribution obviously is 300. Right? Total distribution is 300. Half the distribution. One state has attained that. Therefore, because one state has attained that, it doesn't really matter what the distribution is here. We have system and resource stability. There won't need to be a transference of any resources in this system. Why? Because what ends up happening is, obviously, this is the strongest, this is the weakest. If I intend to attack that, the states just form coalitions. C and D form, and then the combination of C and D form, and then there's defense against A, right? It happens to be the case, however, that it would require all 3 states to form in order to defend itself from A. This is a huge disproportion in power. However, the system doesn't require any transfers of resources, right? And then obviously no one's going to be ejected. A is not going to be, or D is not going to be ejected because there's going to be a 2-part consolidation and coalition alliance formation in order to defend itself against A, right? So it would end up being A versus B, C, D in defense of D, or A versus B, C, D in defense of C, or A versus B, C, D in defense of B, right? Because A versus just B and C isn't enough, right? So it would require all of them to participate in the attack on any of them. Okay.